and get us other results. Among other things, notice that the first bad thing that happens with the polar coordinate representation is if the complex number z can be written as re to the I theta, it can also be written as re to the I theta plus 2 pi k, because every time I change my angle by 2 pi or 360 degrees, I come back to the same point again. At any rate, forgetting about that problem for the time being, notice how I can now define a logarithm for a complex number. In fact, the logarithm will turn out to be the inverse of e to the z, the same as before, but we won't worry about that here either. Let's see how we could define log z from this now. We would like the log to have the usual logarithmic properties. The log of a product should be the sum of the sum of the logs, so log z should be log r plus log e to the I theta plus 2 pi k. Now, r is a positive real number. We already know that the natural log applies there. So what we say is, OK, the log of r is just natural log r. Log e to anything, the log and the e are inverse of one another, so they should cancel, and this should just be I theta plus 2 pi k. In other words, to find the log of the complex number z, you simply take the log of its magnitude and add on as the imaginary part what? The argument, noticing, by the way, that the argument is multi-valued. See, log z is multi-valued. Consequently, we must get into the idea of principal values, and one usually assumes, unless otherwise stated, that the argument is at no greater than pi, but greater than minus pi. If we don't mean that, we have to state that separately. Again, we will drill on that in the exercises. By the way, another application that relates the hyperbolic functions to the trigonometric, to the circular functions, notice that if we wanted to define hyperbolic cosine of ix, mimicking what happened in the real case, this would be e to the ix plus e to the minus ix over 2. We already saw that e to the ix was cosine x plus I sine x. E to the minus ix is e to the I of minus x. That's cosine minus x plus I sine minus x. By the way, I hope that's clear to you. When I say that e to the ix is cosine x plus I sine x, what I really mean is, or even up here, what I really mean is that e to the I anything is cosine of that anything plus I sine of that anything. In particular, if I replace z by minus x, I get e to the I minus x. In other words, minus ix is cosine minus x plus I sine minus x. Okay? And notice that cosine of minus x equals cosine x. Sine minus x is minus sine x. These terms cancel. This becomes 2 cosine x. 2 cosine x divided by 2 is cosine x. And we have the rather amazing identity that cosh ix is cosine x. In other words, a very interesting relationship between the hyperbolic and the circular functions. And by the way, this shouldn't be too surprising. Notice that the circular functions come from studying x squared plus y squared equals 1. The hyperbolic functions come from studying x squared minus y squared equals 1. And x squared minus y squared can be written as x squared plus the quantity iy squared. So what would be a hyperbola in the xy plane would be a circle in the xiy plane, whatever that might be. But again, that's just in the form of an aside. And now we'll come back to what we mean by saying that we can use these new analytic functions to